Good evening and welcome to all of you to the ninth lecture of IPA50 webinar series New Horizons in Physics. As many of you know, this series is held to commemorate 50 years of IPA, and we hope to bring you the recent developments in different fields. The Nobel Prize in 2020 was announced for the astrophysics, and today's talk is given by an eminent astrophysicist in India, who is also director of Indian Institute of Astrophysics, Dr. Annapurni. To coordinate today's lecture, we have a young astrophysicist from National Center for Radio Astronomy of TIFR in Pune, Dr. Bhashwati Bhattacharya. Dr. Bhashwati Bhattacharya did her PhD from IISc and NCRA TIFR in pulsar astrophysics. She was a Marie Curie Fellow at University of Manchester and joined as a faculty at NCRA since 2017. So I now invite Dr. Bhashwati to introduce today's speaker. Bhashwati, you are muted.
Am I audible? Yeah.
Yeah.
So good afternoon, everyone. I thank, first of all, Professor Nadal and the organizers of the series for giving me this opportunity to coordinate this talk by Professor Annapurni Subramaniam. Professor Annapurni Subramaniam has about 3 decades of research experience in astronomy and astrophysics, and she has published about 200 research papers in topics such as star clusters, stellar population, galaxies, and ultraviolet astronomy, some of which we will get to hear today. So currently she is a professor and director at the Indian Institute of Astrophysics. But before the talk, since many of you will like to know a bit more about her journey in the research, Dr. Subramaniam did her PhD from Indian Institute of Astrophysics in 1996. Her thesis was on studies of star clusters and stellar evolution. She then became a postdoctoral fellow at the institute and joined the Indian Institute of Astrophysics and research later on. Right now, she is a director of the institute, as I have already told. So she has mentored a large number of students in her journey, and about 10 have already finished their PhD and some others are working. And in addition, she is also very deeply involved in some of the technical projects. To name a few, one is she has been the calibration scientist for UV imaging telescope called UVIT of India's first space observatory, AstroSat, some of which we will get to know during her talk. She has compiled and predicted the performance of the launch and planned what will happen, like the calibration after the launch. And she also developed the user tools which are necessary for observations with the UVIT. She was also the chair of the Indian team responsible for building the observatory software for 30-meter telescope, abbreviated as TMT, which is built by an international consortium with India as a partner. So over the years, she has been chosen for various awards and fellowships, such as Fellow of Indian Academy of Sciences, Fellow of National Academy of Sciences, and she is life member of Indian Astronomical Union and Astronomical Society of India. She was selected as Kavli Fellow, and which is instituted by Kavli Foundation and NAS, that is National Academy of Sciences, USA. She also received C.V. Raman Young Scientist Award for Physical Sciences. These are some of the awards which she has got. So without further delay, let us now listen to her talk with wonderful title, Astronomy and Astrophysics, Physics, Chemistry and Mathematics of the Universe. Annapurni? Yeah.
Yeah. Hi, Vandana, and hi, Bhashwati. Thanks for inviting me to give it talk under this platform. So I assume that my slide is visible and you
Yes.
can hear me as well. Am I right?
Yeah. Yeah.
Yes.
Yeah, okay. So I wanted to talk about astronomy and astrophysics and connecting it with physics, chemistry, and mathematics of the universe. Of course, astrobiology is left out here, but I am not going to touch that topic. But that's also equally interesting topic. So that way, biology is also connected with astronomy and astrophysics and exploration of how life actually originated on the Earth, etc. So astronomy and astrophysics means like, for me, first thing comes to my mind is the night sky. And night sky would mean a lot of stars and wonderful, patterns in the sky made by the constellations, and looking at the sky to look for comets, which is also there in the picture, or some planets, etc. So this is one of the pictures taken from the southern hemisphere, which actually has a lot of items here. Like you can see a band of things going right across the slide. Many of you know, but when I grew up, and I used to look at the night sky from the place where I grew up, like in a village in Kerala. It was night sky was quite clear, and it was less light pollution. So I could see the structure. I never knew what it was. But now everybody knows, thanks to information available on your fingertips, this is the Milky Way. And you can see that it has got a patch of like black or dark stuff out here, and along with a lot of a bunch of stars in different colors out here, and then some bright stars and little less stars and two patchy stuff out here. I assume that you can see my cursor moving. The
Yes, cursor is visible.
yeah, okay. So the comet is also out here. So the point is, these dark things out here, you can have dark things in your picture when you don't have a light, or when the light is being blocked by a particular um, uh, 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 something is blocking the light. So in this case, it's the light being blocked. So we know that there is some material which is intervening material between us, the viewers, and some light emitting source behind it. So we now know that these are the interstellar gas and clouds in our galaxy. So which would mean that the galaxy has got some structure, and the galaxy has something like what is basically like the why is it holding up, like what is creating it as a structure, and what are the components of it, and why are they the way they are. So I would like to talk to you about these things, and also in general the interest on why do we have to study, why is it important to study this topic of astronomy and astrophysics. um, so this is the fascinating night sky, and nowadays with the digital cameras, astrophotography is it's very popular, and people take pictures using various gadgets, right from your cell phone to a sophisticated camera. So this is one of the very beautiful pictures taken by Angchuk. This is from our the observatory, which is located in the Himalayas in a region called Leh, and this is in Hanle. And you can see the same Milky Way which is there in the picture in a grand detail. So it is beautiful. And this also brings us the same patches I showed you that I was mentioning about. And also you can see this, filamentary structures, and some are bright and some are dark, and the bright regions are really bright, telling us that something is very luminous there. So something is very bright out there. So this tells us that there is a structure out here. So these days, night skies, the fascination for night sky is captured through astrophotography. There are many people who want to go to dark sites and take pictures, since in city lights you cannot go out and see beautiful sky. So for me, when I got passionate about astronomy, I go out in the night and just stare at the night sky. It's be really beautiful. So that is something which we experience in nature. Why the nature itself presents in the form of various patterns in the night, in the sky, right? So how did we as humans start getting interested in here? So I will also come to it, and why the astronomy is it still relevant, and do we have to still look at the sky for the same reason when we started looking up this sky? So I will come to these points, but right now we have been captured by the recent Nobel Prize announcement. So we all know that three people were awarded Nobel Prize in Physics for this year, and Roger Penrose got for the discovery that black hole formation is a robust prediction of the general theory of relativity. So that is one half is the theoretical prediction, and second, Gensel and Guess got it for the discovery of a supermassive compact object at the center of our galaxy. So I would like to, I mean, the citations are out here. So black hole has become a word which anybody would use. Like the students are extremely fascinated by the topic or subject black hole. And everybody knows about it because we now talk about mergers of black holes, detection of gravitational waves, and various other things are already there in the picture. So this award is an recognition of the theoretical prediction of that, as well as the detection of an object which has similar properties of what you expect for a black hole. So I would like to show you something like what it was and how it is done. So this is Andrew Guy's work, and also what happened was in the center of our Milky Way is where this compact black object was detected. Now people always ask this question like, what do you mean by detecting a black hole? Everyone tells us that you can't see a black hole. Now how is it possible for someone to detect a black hole? How is it done? So it's just a bit contradictory, isn't it? So in order to make you understand what do you mean by detection, or how do you detect a black hole, you are not detecting it, you are indirectly inferring the presence of something. So that is what happens here. So I would like to show that. And this is the galactic center. This is at the group at the UCLA, this is the University of California at Los Angeles. Now, at the Galactic Center, you can detect objects, which is like towards this one of the Sagittarius in the Milky Way band. Now, you can see that the patchy. Why is it patchy in this direction? You are looking at the plane of the a disk which is like inclined, and you're looking through it. Now, if you're looking through it, you're looking through all the pollutions, all the dark stuff there, which is basically the clouds and the dust and everything. So visible light will be attenuated. It's like, if you are in a very hazy morning, the light, your visibility is completely reduced. Similarly, here also visibility is completely reduced. So you cannot use visible light, or the light emitted by stars near the center of the galaxy will not reach you because in the visible wavelength, because it gets attenuated and they just die off. But that is the property of the particles in between, right? It's like the scattering, so absorption, etc. So if you want to see this place with all the details of how many stars are around the center, you have to do two things. One is you have to at least see, or detect. So some wavelength, some photons have to reach you. So it is known that the photons in the infrared wavelength, they don't get attenuated much. So infrared is a better band where you get to receive the photons, where on the other hand, the optical photons get truncated and you don't even get them. So you have to look at them in the infrared band, number one. Two, it is so crowded and it's far away. So you have to kind of resolve these individual stars so that you know how they are moving with respect to the central, anything what is there in the center. So you need to have techniques to make sure that you have better resolution. So they use the adaptive optics techniques. So that is That's an important thing which we have understood, how to get rid of the atmospheric turbulences which is happening in our atmosphere, which actually blurs your image. So you have to have extremely clear image to aim the infrared to detect it. So that is what Andrea has and her team have done together. And now I would like to show you a movie which they have put together. It's in the public domain in their own website. So I'll just stop share and go to the video and tell you how that is done. So this is the video they have put together. So you can see this is the central. This is inferred central. Apparently, looks like there is a central thing there, which you basically infer from the motion of stars around it. So what actually happens is you start mapping it over the period of time. So the number which is shown here on top is the years. So you take a picture. So let me go and the beginning and then start showing you from the beginning. So this is the location of individual stars like S0, S1, S02, etc. at the time 1995. Now you take a next image and then, you know, every year you take an image and start tracing where the star has moved. Now the lines show where the star has moved over the time. So every year or every during take a set of durations and keep visiting the same place. And then you start seeing that some of the stars are moving with respect to its previous position. So over the time scale, you can see that it has taken a long time to map the same region and trace their actual motion. So now this is a 3D motion, which is basically looking like on the sky, how the stars are moving with respect to each other. It's a very long duration. It's more than 10 years. And this orbit is the most important one, where you know from the laws of motion, you can actually find out what is the one of the focus of this ellipse, and that is the star which is shown here. And you're not detecting the black hole, you're detecting a focus where the velocity and the orbital parameters of it tells you how much massive this particular object should be to close this orbit within 15 years. Now you should remember that the sun, which goes around the center of the galaxy, takes about 200 million years to make one orbit. So this is done in 15 years, which would mean that the orbit is very small and the mass has to be very big. So that is how we estimate the mass of the black hole and presence of some compact object. So it is not the black hole, we still detect a compact object. Now, you also get the radial velocity, which they have made the 3D movie. So you also can go and see that. Maybe I can just stop it's just this. So 3D movie is possible because you can see the motion in the plane of the sky. That is the 2D picture. Now this is the radial velocity. Once you have all the three, this velocity and this velocity, you can actually get the vector on the 3D space. So that is what this orbit is all about. So it's a lot of hard work. And actual images will be looking like this. So this is also important for you to understand. So these are the images, you can see them. It is like, it's the movement of the positions. That is how you take it. This is basically a time series of all the photographs taken. This can give you a real picture. Now you trace the location of the star, you're going back and forth, right? So that is how it is done. And we are not seeing a black hole. We are inferring the presence of not even a black hole, a compact object out here, which fits the bill of exactly what is the prediction. Okay, so that is the importance, and there's a lot of hard work with respect to a lot of long duration and the techniques involved. That is very important here. Okay, let me go back to my talk. I lost it. Give me a minute. Yeah, okay. Yeah. So that is the importance of this. Now, coming to the question of um, why do we study this and what is the use, and do we actually use the sky for our survival as of today? Because humans, when started looking at understanding the sky and astronomy, the requirement was of, basically on two topics. One, for time, basically to see whether it's morning, night, or evening, or in the night also it is early part of the night, or it's how many hours more to become morning, etc., etc. The other thing was direction. If you are navigating in a night and going from one place to the other on land or in the sea, you need to know your stars. You need to know the sky. It is one of the requirement, because then only you will know the directions, and you will know that which constellation comes in which direction. So this is the east, that's the west. This constellation is setting, so it must be the time, or this must be the month, etc., etc. So that is important. Now, do we need to know to look at the sky to know the directions? No, we actually look down where into your mobile. So open the Google Maps and see, open the map, and it tells you where you are and how you need to go. Now, how is that happening? That's happening because there is GPS, and GPS tells you that there is where are you with respect to a particular place, and then takes the map and plots it. Now, this is done by GPS tracking is done by a constellation of satellites which move around the galaxy. Now, in that case, the two satellites actually position you, and by triangulation method, they actually tell you where you are with respect to them, these two satellites. Now, let me tell you one thing. The satellites are going around the Earth is going around the sun is going around the galaxy, and the galaxy is in the long run moving somewhere else. So now, is anything stationary? No, nothing is stationary. So how the hell is the satellite's going to know where they are with respect to the whole framework to position you? So have you thought about this? So in order to locate themselves, these satellites need something else. What do they need? They need the outer, that is the outside the solar system. They need outside stars, and the stars also move. We have seen that the entire stars, including the sun, move around the galaxy. They want something which is much farther away. If you look at stars in the external galaxy, they're too faint, so you cannot use them. So astronomers have suggested quasars, which are the very bright up in the sky, which are very small single point sources, which are very far away. Practically, you can see take them as not moving at all. So it takes quasars to locate these satellites. So what is happening? We have outsourced looking at the sky to something else. So the gadgets do it on our behalf. So looking at the sky is still important for positioning us on day-to-day basis on the Earth. So it's extremely relevant. And in next decades to come, if you're doing an interplanetary space exploration, you have to have a coordinate. You need to have a system to understand where you're going, what is the path, where it is located. So extremely important to have a framework which is given by the stars and these galaxies. So it's very important. Astronomy and these studies of them are very, very important and extremely relevant even today, and it is affecting our daily schedule as well, right? Everything what we do. So it is given a lot of stuff for our easiness for the society and for everybody. So there is a lot of things which astronomy has led in terms of technology, wireless, cameras in the aerospace sector, in the energy sector, medicine, etc. These are listed in the International Astronomical Union website. You're welcome to go there and take a look at it. So if someone asks you, why do you want to do this? So it's though it is not apparent, it is quite embedded, and many things you can know from this particular website. And second, what do we do? So I am at the Indian Institute of Astrophysics, and our headquarters is over here in Bangalore. It is located here in Karnataka. We have an observatory in the Indian Astronomical Observatory in Hanle, which is out here. And we have this is our northern observatory. The southern observatory is in Kavalur, and we have a outside campus at Hosakote, which is about 30 kilometers away, where we have that is the place where we control the telescope. Nobody goes there to take the data. Everybody just goes here, and through a satellite link, this telescope is controlled. And we have a radio observation facility at Gauri Bidanur. And we also have the one of the space telescopes, that is ultraviolet imaging telescope on AstroSat, is built in the Crest campus here. And this mission, AstroSat has completed 5 years in orbit in September. And the UV imaging telescope is operated from, or its payload operation center is in this campus. And to give you a feel, this particular spacecraft goes above Bangalore once in 90 minutes. It's got a 90-minute orbit. So you can imagine how fast it's moving. Every once in 90 minutes, it goes over Bangalore. Okay. Now, these are some of the pictures of our campuses. This is the Hanle campus, where we have the 2-meter telescope and another smaller telescope, 70-centimeter growth telescope. This is the Hosakote campus, where we have the remote observing facility. And this is the same place where this UVIT was integrated. This is our Kavalur campus. This is the Gauri Bidanur dipoles for study of the solar radio emission. And these are 2 telescopes in our Kavalur site. And this is the whole AstroSat getting tested in the ISRO center. And this is the Kodaikanal, where we have this is solar tunnel telescope. So these are various facilities. In case if you are in all the details about these facilities are available in our website. Welcome to go and take a look at it. Now, what do we kind of study? We kind of study various types of stars, types of galaxies. There are different types of things. I am interested in groups of stars, and we study how they are formed, and they give us an understanding of how stars evolve and what kind of things they produce. Now, the million-dollar question you will now have in your head is, why the heck should I study? If I study one star, why should I go and study another star? All stars are stars. If I study one galaxy, why should I go and study another galaxy? Every galaxy is a galaxy, right? So what is so big deal about it? So now I would like to tell you something that this is, I don't think you need any introduction to this. This is the periodic table. And we have celebrated the 150 years of Mendeleev's periodic table. And all these elements in the universe, who created these elements? Now, all these elements you see in the universe are all created by stars. Now, this particular slide tells you which are the chemicals coming from the Big Bang, and which are the chemicals coming from various other types of mechanism. Most of them coming from large stars, small stars, supernovae, and man-made. Man-made being at the very end, the massive ones, which are quite unstable as well. Now, how are these produced in stars? Stars are then nothing but nuclear reactors. Of course, they are nuclear reactors. We know that the sun is producing energy by fusing hydrogen to helium, and the core in the sun is now getting filled by helium, and the hydrogen is in the outer layer. So hydrogen is the most abundant one. So now you have to convert hydrogen to helium, and then helium to carbon, the carbon to nitrogen and oxygen, etc., right? So that is how it goes. Now, what actually happens is, like if the star is very small, the temperatures it can reach at the cores are not very high to start fusing the larger nuclei. But if you have larger stars, like in green, what you could happen is, these, if assume that you have a star which is 10 times the size of the sun, or mass of the sun, then you have much more dense matter, and then it can actually heat up a lot more in the center. So you initially convert it into the helium, and then the helium collapses and then heats up, and then it is hot enough to convert it into carbon, and then again the carbon becomes very heavy that it cannot support its own gravity. It collapses, heats up to start the fusion to the next one. So you can imagine the star to be creating through its evolution layers and layers of various elements, as shown in this particular table. Now, at some point, it'll reach iron at the core, and you have series of other elements in layers. And this is called the onion skin model, where we think that the whole plasma has layers of material, and if some of the material actually through mixing can appear in the surface of the stars as well. So all that we can study by looking at the star is the surface, and the surface, you take the spectrum of the light coming from the surface, will tell you what are the elements present in the surface. Now in the big stars, some amount of mixing can happen and some of these elements are present. So a stellar spectroscopy tells us what kind of elements could be there, which is getting built in the center or inner regions and brought up through convection because it mixes. Now, when the star eventually faces the last, like a 10 solar mass star, what happens is this ion cannot fuse anything more because it needs more energy. So it basically collapses under its own gravity, and we know that it becomes a neutron star. And then when that happens, when the collapse happens, is actually a implosion, and then the energy released in the implosion lifts up the entire outer region, and you can see how many various types of elements are there, and these all matter gets kind of mixed into the interstellar medium. So you have a mixing of all these things. So the stars, a generation of stars which are formed actually creates a lot of material inside them, and they throw it out into the surrounding medium. And now surrounding medium is full of other gas. So they mix these things, and then the next generation of stars form. So the star basically produces a wide variety of elements. Now, when such a star, one of the stars inside this complex of star formation bursts into a supernova, the new elements produced get mixed up, and then the second generation has much more more in particles of all these elements per unit volume. So these regions where do they happen? They are formed in the disk of the galaxy. So you have gas, just like you saw in the first picture, the dark bands, where these are called the pillars of creation. So this is a zoomed in picture of one such star forming region. You can see that the bright edges tell you that there's some light is escaping from the inner one, and there could be massive stars inside. So you have in the galaxy gas, dust, they could be diffuse, clouds of different size, they could be ionized, they could be molecular, they could be atomic. Mostly these gas have hydrogen and traces of other elements, and they are of big sizes to small sizes. They could be doing all kinds of scattering, which we use to study these molecules in the interstellar medium, the medium between the stars, and they mostly emit in the infrared. So the entire ecology of stars forming, dying, etc., and the stars, long-lived stars existing, all are happening in the galactic disk itself. So we need to understand what the disk, how the galaxy has formed, and how these each region of the galaxy has different types of chemistry or dynamics based on what kind of processes it has gone through, etc. So that is a matter of understanding. So this is the galactic ecology. You have the molecule, the clouds, which are atomic in nature. Then they become molecular. When they cool down, they become molecular, and then they become very dense. And then once the star formation starts, you have various types of stars formed, and then the big stars explode as supernovae in very short time scale, and the ejecta, this is the ejecta, and they get mixed with this thing, and then they say the star cycle happens. Now, the questions which one raises that when you see a galaxy, can this happen at all the places? No, we don't see that. And can all the galaxies go through the same set of cycles? No, we don't see that. So what happens is, it's in order to have sustained the cycle to be sustained, you need to have material being being driven, and you need to have the gas to start this, and you have to have methods where you have hydrogen clouds, but they may or may not be able to convert into molecular clouds. And the molecular clouds may be sometimes triggered to form star formation, sometimes they live longer and do star formation spontaneous. Sometimes suddenly they start forming stars, so there's a delay. But in some places you do get star formation because of shocks, because of triggers, because of mergers, etc. So there's a variety of things which are happening which is not standard. So you cannot say that this is the cycle which will be present everywhere. Every part of the cycle gets changed from place to place. So it's not that if you see something around the sun, it will happen everywhere. It is not like that. So that is the reason why we have to study what happens in different parts of our own galaxy, because this may not be true what we see in one place. And second, in other galaxies, some galaxies we see that there are a lot of gas but there are very little stars. In some other galaxies we see that full of stars, there's no gas. So what happened there? So they present to us wide variety of environments, so which tells us that there is a wide variety out there. We need to understand the physical mechanisms which go into it, and there's a lot of chemistry involved here, because the formation of elements, how they get mixed, how they become molecular, etc., etc. So that is the thing. And second, the third is the mathematics in terms of, you know, all these governs equations of cooling. You have to, they're all part of the hydrodynamics, and magnetic field gets involved in it. So magnetohydrodynamics is to be there. You have to solve a lot of equations to actually get a complete physical picture of it. So it's a kind of a mixture of physics, chemistry, and mathematics going together into it. So this is a big picture, like the same thing. So you can see that the star formation, this is the spiral structure. The spiral structure is eye-catching because they're bright and there are more stars are being formed there, and you can clearly see that the matter is kind of preferentially distributed in these places. And now you need to understand why is it happening? Why is the matter getting distributed preferentially in spiral lamp? What is the physics of spiral arm? How do you solve a continuity equation if you have matter which is going around the galaxy, etc.? So these are questions which still do not have definite answers, because if you see this galaxy, it doesn't have a bar, but in many galaxies, if you see, there'll be a big bar, and then the spiral arm start from here. So what decides when during the evolution of the galaxy it becomes a spiral galaxy or a barred spiral galaxy? It still we do not know. So there are still open questions. And as I said, this is the view of our Milky Way. You can see that the different wavelengths give you different pictures of various things. So this you can see right from here, it's a radio emission, then the atomic hydrogen, 20 centimeter, there's a radio continuum, the molecular hydrogen. So if you want to trace various things, you need to use various probes. So infrared looks at emission from warm dust, hot dust, and stars. Radio, on the other hand, looks at 21 centimeter, that is the atomic hydrogen and the radiation from charged particles. X-rays give you a picture of supernovae remnants, pulsars, star forming regions, etc. So the wavelength you choose to study and the objects which you want to study are well connected, because the formation of photons from there has a particular process, and that photon has a particular energy. And if you want to study that particular process, you have to tap that particular photon. So you need to have a detection mechanism to detect that particular photon of that energy. Now you have to define, you have to create a detector, you have to create a mechanism to collect it. So that is how the telescopes, and you have wide variety of telescopes and detector systems are required to capture the different types of photons in different wavelengths and understand how we can study what is out there. The only thing in astronomy we can get is the photon, detection of photon. So how do we get it? How smartly we collect it? How smartly we analyze will tell us more about the object we are studying. So in half of the cases, you can do it from the ground, and half of them you cannot, because the atmosphere blocks most of the light. So high energy photons, you have to go up above the atmosphere, and then only you will get them. You even capture them. And optical and near infrared you can do from the ground, but mid and mid infrared you can't do it. So in the near infrared, you can see that the galactic center clearly, optical, you can see this particular image is completely blocked but you can see this near infrared, which is very bright, and which would mean that you are able to see the most of the light coming from the central region. And that is the reason why I mentioned in the beginning of the talk that the infrared is required to probe the stars which are near the very center of our galaxy. Now, we also use this kind of a diagram to understand the different types of stars, which is nothing but the luminosity. The total energy emitted is on the y-axis, and the temperature of a particular object. That gives us understanding of course, classification, right? So any science you take, you have to classify them, group them, and then study their properties. So astronomers also do this, and this is the fundamental diagram which we understand. We use to understand the evolutionary sequences and overall why they evolve, and what sort of stars you do have in this near the sun, why certain stars are not found near the sun, etc. So this is our astronomy. Astronomers majorly use this diagram called the HR diagram. Is done by Hertzsprung and Russell. So this diagram is very important to study two things, and you also can convert into an observable plane. So you have a theoretical plane, and all the models you develop regarding stellar evolution, etc., will be tested here. In case when you don't see stars but groups of stars, like if you want to go to a galaxy and see the kind of patches out here are not single stars, they are groups of stars. So now if you want to model that, you have to predict that this particular group has about 1,000 stars, and these 1,000 stars will emit differently, and you combine all the light and predict what kind of a dominant population is right out here. So in order to do that, you combine everything together and do it. So single star evolution is very important to know, and when you have to go and talk about groups of stars in external systems. Now, I already talked about it. So this is the galactic structure. Now, structurally, dynamically, this is important because we know that our galaxy is a spiral galaxy. Spiral galaxies are disk galaxies where it's a very thin disk where all the material, gas, dust, and stars are distributed, but the central region has got a bulge. It has got a kind of a very non-luminous but very important halo around it, where you also have dark matter. And this halo is not very visible because density is the number of stars per unit volume is very less, but that's nevertheless it's present. And the stars in the halo have different orbits, and the stars in the disk have different orbits, the stars in the bulge have different orbits. Now the question is how the whole thing is stable, because sun has not gone very much in closer to the galaxy or far away from the galaxy over the years of its life. So how is the whole thing stable? How is it things are not colliding? Where do actually stars collide? Or are they all collisional systems or collisional systems, etc.? So these are important stuff. There are regions where you look at globular clusters, they collide, okay? And these are the kind of, in the disk, if you see in the thin disk, the stars go up and down. So this is the kind of orbit you see. They go around typically like this, but then there'll be a slight up and down movement as well. But because this within the scale height, in general, the scale height is very thin for our galaxy. So this is the kind of problems we study. And on the other hand, these globular clusters, and also with respect to the center of the halo stars galaxy, the halo stars go in elliptical orbits, and in such dense systems, we encounter a wide variety of density. This is one such object. It's a globular cluster in the halo. Halo as such is very dense, but within this globular cluster, the density is very high. So within these systems, you have to treat the particles as collisional systems. So they actually collide. And we do have evidences of collisional mergers or scattering, ripping apart the stars. So those kind of things happen over here. So we deal with wide variety of densities, wide variety of parameter space to understand dynamical terms. Now, distance is another important thing where people, without which we cannot understand the luminosity, and this is the primary distance measurements. And now I should also mention that Gaia, which is a mission from European Space Observatory, has measured it for up to about tens of kiloparsec, the distances through parallax measurement. So parallax is the absolutely primary method to find out the distance. Then we look at other objects like variable stars like Cepheids or supernovae, which tells us how far the galaxies are. So, but we have to build that distance ladder based on the nearby stars, and their distances are actually estimated using parallaxes. So when you talk about a very far away thing and you have estimated distance, it is not direct estimation, but then it has built up that secondary calibrator is built up based on the nearby things. So it's a robust one. So you find the nearby stars, then you apply to the next one, and then you go. So you step by step go, and then find the distance to the farthest one. That's how it happens here. Just want to spend a few minutes on AstroSat and how we have gained expertise in the space astronomy area and operations and launching and supporting operations. So all these are led by Indian institutions, as you can see, and UVIT is led by the Indian Institute of Astrophysics. Now, this is the kind of payload we have built, and one important thing is what is so big about building space missions, space satellites. The important thing is the same reason that those photons do not reach onto the ground, because the molecules absorb them. So if you want to stop this absorption, whatever you are creating should also be free from this contamination, right? So if you put a tube like this full of molecules up in the above the atmosphere, the photons entering the tube will not reach the detector. Within the tube itself, it gets absorbed, right? So you have to have minimal contamination. So when you are building the aircraft and sending up, while building itself, it has to be contamination free. So contamination free environments and entire things should not be producing contamination. That's a new lesson learned. And how do we put it together and launch it and make it work? So that was we also created these kind of spaces, clean room facilities, huge laboratories where you can actually integrate. That is there in a campus. So these are the pictures taken over there. And this is being improved, and we are also aiming to launch the next space mission or to study the sun. That's the Aditya L1 mission. We also have to shake the whole thing, because if you have a backyard instrument, if something goes wrong, you can go there, remove that particular part and fix it. Now this you cannot do. On top of it, when you are lifting off, the rocket shakes. So you have to make sure that even in that shake, your things are not broken. So this is done a priori by a shaker, and after shaking, your engineering model is shaken, and make sure that the parts are not broken and your electronics are not broken, all the cable connections are not broken, and the mirrors are not broken, etc. So these tests are done. So environmental tests are very important before you launch a payload. And also thermal cycles. It goes through, as I said, it goes around the Earth once in 90 minutes. So it faces the sun, then it comes to a night, but the dark part of the Earth where it doesn't see the sun. So the temperature through its path changes drastically. So it has to go through these cycles prior to being there to make sure that the system can take care of this thermal cycle. So these are the kind of tests you need to perform before it is launched. So that's all done. And this is the integrated payload, which is being put together with the other missions. And you can see it's fairly big, absolutely big. And the whole thing is lifted, and it is going around the Earth like this for last 5 years. So it's of immense pride for us to have done this, and it is still working, producing excellent science. Now, what do we do? So this is put on the PSLV C30. Now, if you take a picture of the entire, I stare at a particular object and take a picture for about 10 minutes, and take an image and look at it, you see this. What is this? It's got a signature, right? So what is the signature? You can imagine that while it is moving, it is locked onto a particular location in the sky because that is where this object is. Now it cannot be absolutely shake free, right? It is shaken. So that is what it means. So we do the post-processing. One of the important things we need to post-process in terms of space missions is this drift correction. So once you correct the drift, this is what we get. So this is the image which has been shown for the last 5 years very proudly by the astronomical community, where this particular object was one of the first objects observed 5 years back, but this was the same object observed by the previous NASA mission, Galax. So you can see how clearly we have imaged it, and that literally opened our eyes and said that, of course, yes, we have a world-class facility up there. So since then, we have been doing excellent work, and the instrument is also functioning well. So these are some of the images. This is one of the jellyfish galaxy, which is falling into a cluster of galaxies where you can see the material being stripped out of the galaxy, and this material that is stripped is forming stars. So these are called jellyfish galaxies, and there's a huge zoo of stuff out there. Very, very nice pictures. And these are some of my work, where you can see this is the optical picture of a globular cluster, but you can see the center has a lot of exotic stars formed because of these collisions, which I was talking about, because it's a collision system. And if you want to study them and what kind of zoo of stars you have, it's too crowded in optical. But if you look at it in the UV, the entire crowding goes, and you can individually count the stars out here. It's brilliant, right? So we study the hot stellar population in these stars which are emitting in the UV. So in some cases, you can actually completely see without any crowding. So these are the kind of some of the science I do. So I stop here. Thank you, and I look forward to hear your questions.
Am I audible? Yeah. Thank you, Annapurni, for the very enlightening talk. We already have quite a few questions. Let us first start with Vivesh, and he is in Zoom, so he can unmute himself and ask the question probably. Vivesh, are you there, or should I? Okay.
I can see it in the chat. Should I read it out?
Yes, maybe. Yeah, you can read. Okay, Vivesh is there to ask.
Yeah, I can ask.
Yeah.
Look, in the outer galaxy and the stars, many of the elements are found, like hydrogen, helium. There are evidences. But do you have any? Up to what heavy elements are found in the outer stars, in the outer galaxy, and do we get heavy elements like uranium, neptunium, plutonium, etc.?
I'll just go back to my share, and then I'll just let me. Okay, I'm not able to. I'll just do one thing. I'll. Okay, let me tell you. So what happens is in the core, by fusion we make most of the elements.
Yeah.
But it's not only fusion. It is like, as I said in the in my presentation, this is what I want to show you, right? So you can go up to iron, but what happens after iron? Many elements are also produced in supernovae and stars, right? So how do they get produced? So we have two types of elements called slow neutron capture elements. So within these, during the nuclear reactions happening in different layers, a large number of neutrons get generated. As you know, in a nuclear reactor, you have to capture neutrons. A controlled reaction has to happen, right? So when you have a large number of neutrons present, these neutron capture happens and nuclear reactions take place. That ends up in producing heavier elements as well. So the other bigger ones are converted into, other produced because of neutron capture in supernovae as well as in terms of inside the star as well. And now your other question of uranium, yes, that is also present, but in the stellar, not in the interstellar medium, but is found in the star surface because of these neutron capture and mixing, and they come to the surface. And those are important to understand the formation mechanism of these elements, which get eventually thrown out into the interstellar medium. You also do a chronological study based on the isotope ratios of these various elements to understand what sort of neutron sources and flux strength you have in various reaction scenarios for their production. So does it answer your question?
Yes, but how do you actually detect all those things? You do by mass spectroscopy method or some other ways?
Yeah, so we do spectroscopy. So we take we put the, telescope. You put the, you kind of point to the star and put the slit, and the light from the star is taken to a high resolution spectrometer. So high resolution spectrograph. In many cases, the spectrograph is equipped with high resolution grating. So you can go up to 40,000 resolution or 100,000 resolution and split everything up. So lithium 6 to lithium 7 you can measure it. And you have very complicated, very sophisticated models to generate. So you have taken a spectra and you have observed spectrum, but then how do you know what is what, right? And what conditions you do it. So you also have various models where it takes all the atomic transition scales, temperature, conditions, etc., and produces the entire spectrum. So that is compared to estimate or actually estimate the content of each element.
So it's optical spectroscopy.
Optical, people have done it in the UV. FUSE is a high resolution spectrograph in the UV. It's a space-based. Optical is ground-based, also near infrared.
Yeah, so sorry, I meant actually
A lot of lines and molecular lines.
Sorry, atomic or molecular lines. That's what I should.
Atomic. Yeah. So if you're going to UV, then you're looking at a completely ionized.
Okay.
You have multiple lines of ionization. In the optical, depending upon the temperature of the star, you can expect certain lines. And if you're looking at cooler stars, then you will get only molecular lines. So your database has to have everything, or you have to choose the database according to what kind of a star it is, what temperature it is, what kind of an ionization states you expect out there, and then do it.
Yeah. So now there are many questions in YouTube. So maybe we can go through those one by one. So first question was from Basavraj. So question 1, he has actually 3 questions, but we'll take in sequence. So first question from Basavraj is, could you comment on the composition, size, the formation, and the distribution of dust in galaxy?
Okay. That itself is a very complex question, and it actually is got the thing for a whole one talk. So how is the dust formed? So that's a fundamental question. So in general, we think that the dust is formed while during the stellar wind from the low mass stars, where actually the envelopes lift off. We have seen nucleation and star dust coming out using carbonated dust in certain types of stars. C60 molecules are found. So these cool down and progressively make it is nucleate and make larger things, is what we understand. And then when they cool down and get into the interstellar medium, they grow. And we also know that once you have a complex molecule, even the surface of that complex molecule in certain conditions can be nucleating for smaller molecules around it. So a huge set of studies regarding dust is a completely, it's a kind of a field by itself. We see the polyaromatic hydrocarbons, PAH molecules, are very important. And any near-infrared spectra and any near-infrared bands which you choose up to 24 micron have a lot of very interesting molecular features there, which we think are due to certain PAH and silicon molecules. I'm not very confident, but then there are a lot of them there. So star formation regions, if you see, they used there. You can have them in emission, but they also can in absorption. So depending upon whether they're in emission, then you get their temperature profiles. And if you look at CO molecules, that is there in the millimeter wave. And that is how we actually get to understand the molecular hydrogen properties, because we don't trace the molecular hydrogen directly. So it's a field by itself. It's a huge thing, yeah. And of course, it's a very important component.
Yes. So, Anna, yeah. Sorry, Annapurni, you are not audible. Hello?
Hello?
Yeah. Now it's okay.
Yeah.
So the next question from Basavraj himself is, could you comment on the formation of globular clusters? Could there be a black hole at its center?
Yeah, okay. So globular clusters formation, as we understand now, I mean, the globular clusters, as I say, is in the framework of our galaxy, is an old cluster consisting of very low mass stars, and mass is less than the sun, and typically of the age of about 12 giga-years kind of a thing. And those clusters are thought to have formed in the early big blob of our galaxy. When it was during the formation time, there were many clusters were formed, and they got kinematically decoupled when the whole blob got a rotation, and then the entire because of the rotation, it became a spiral plane kind of thing. That's what the traditional thing which we understand. But we thought we understood everything about the globular clusters, but nowadays we know that it is actually it's not single stellar population. We see that there are multiple population out there. There are variation in chemistry among the stars, etc. And the other point which was of interest, like the compact object, is that it's a dense system. So why there's no black hole out there in the center? We have seen millisecond pulsars. We can see, we have seen binaries, we have neutron stars, right? So why not black holes? We have not seen them. We have seen a lot of binaries, and we also know that the dynamical systems go through they have a collapse and post-collapse core collapse happens in these systems. Dynamics is very crazy out here, because you actually have inner part becoming dense and dense because of relaxation, dynamic relaxation, but it doesn't collapse. It bounces back thanks to binaries out there. But we haven't convincingly got black hole at the center of these systems as such as of now. There are cases, there are candidates, but not yet.
Okay. Yeah. So maybe we can go to the next question by Shubodh Kumar Godre. There are actually lots of questions. Yeah. So the question is, there may be many lighter mass black holes in our galaxy. Is there only one supermassive black hole in our Milky Way galaxy, or more?
Yeah, so that's very interesting. We have seen or detected the presence of one supermassive black hole so far, and we think that's it. We don't know whether it doesn't have a double nucleus, or we have not seen such features. If we have two supermassive black holes, we haven't got any signatures or any clues for such an existence. We have only seen felt the presence of one. Of course, there are stellar mass black holes. There are a lot of them, and we do study them using X-rays and other binary systems. They are in binary systems, stellar mass black holes. So they are there in the binary system. But we are talking about at the center. But as of now, we know only of one.
So that answers his question. So the next question is by PM Rangarajan, and the question is, the center of our galaxy is very far away. He has written the light years. But from astronomical proportions, this looks like a short distance. Then why the gravitational waves are not detected in LIGO? So should I repeat the question? The question is...
The gravitational waves, so you have to create a wave, then only you can detect it, right? Just a black hole being there is not creating a wave. So you have to create a ripple. It's like you have to put a stone in the water, then only it will create a ripple, right? So something has to happen, then only you will get a wave. Just a black hole being there is not going to create a wave.
So the next question is from, again, PM Rangarajan. Is NASA has identified an asteroid called Psyche 16, which is made of iron and steel. And this is not a question, this is kind of comment. So, okay, this can be there and people can look at it. We can go to the next question maybe. The next question is again from Shubodh Kumar. The supermassive object was inferred from orbiting stars as mentioned. This object must be having an accretion disk. Is it seen? So his question is if the accretion disk is being seen.
Yeah. We haven't seen the accretion disk as such, because accretion disk, you can see if there is a matter being accreted. So maybe that there is no matter being accreted as of now, or rather when we get a signal, we interpret it as accretion disk. Or we do see now, you probably would have seen in news about the tidal disruption events. People have seen the flare, etc., or a blob, which is the blob of dust which is coming out of a black hole, etc. So that tells us that the time scale of eating up, how do you actually spaghettify or disrupt the star and do gobble it up, or rather falls into the black hole. So that kind of events we have done. But like the active galactic nuclei, you do have huge accretion disk, etc. We don't have such it's not an AGN, right? So we don't have an active nuclei at the center. So maybe because of that, but it doesn't show any signatures of having a accretion disk.
Yes. So the next question goes like this. Could you comment on distribution of dark matter in our galaxy, especially near the center of our galaxy, by Vashavraj?
Yeah, so I don't have the slide for that, but we have inferred the dark matter distribution. Basically, it comes from the velocity, estimating the velocity, and that velocity in the orbit, just like the same concept which you use to measure the mass of the compact object. You can find a particle which is orbiting to very far away place from the center of the galaxy, and find out what velocity it is moving and what is the enclosed mass within that particular orbit. Now, if you convert the visible light to a particular matter, or whatever emitted, detectable in all wavelengths you put together, and convert it into a mass, that mass is completely falls short of the mass which is shown by that particle. So kinematically, it's robust because it is saying that mass, and that is the reason why it is moving with that velocity. Now, how is that mass? That is what the visible mass minus, there is something which out there which is not emitting any photons, which is not detectable, but it is experienced. So that is why it is called the dark matter. Of course, there is a distribution, but there have been models which say that there is a difference in density. It is flattened, and there's a difference in the density between the center to the edge, etc. But I'm not an expert in this field, so I do not know what is the present status of the structure of the dark matter distribution within a galaxy from the center to the edge. But it doesn't seem to be a uniform distribution.
So that answers Bashavraj's question. So next is a comment by PM Rangarajan that he's very proud of your achievement. All of us are. And the next question comes like, these works of Indian satellites give another mileage to Aryabhatta and Bhaskaracharya. Where can I get these photos? I don't know which photos he mean.
Yeah.
Photos of maybe the slides or
photos.
the satellites. Yeah.
Astrosat.
The ISRO has a website and for Astrosat, and you can actually look at many of these. There's something. There used to be something called Astrosat Picture of the Month. They have about 24 pictures out there, and there are many official picture releases from ISRO, including the recent result from UVIT, which came in Nature paper, Nature Astronomy. So that is also available. So please take a look at ISRO's website. Please search ISRO and Astrosat together. It'll take you to that page, and then there are a lot of pictures available out there. And there's a website in our website. I'm not sure how. We have also some gallery where images are available in the Institute of Astrophysics web page.
In the IIA web page.
IA web pages.
Okay. So then Srikant, you can look at that. So let us go to the next question. Is by Narayan Das. He is saying, Madam, what is the source of dark energy? I mean, what field creates this energy? That is his question.
I think you should read up on that from any popular article, because it's very difficult. I mean, it takes some time to introduce that concept and explain it.
Okay. So the next question is kind of a generic question. What is your advice for young teenagers and students who wants to become astrophysicists?
Okay. Yeah. So what I would suggest is that this field is very, very interesting, and a lot of nice. The next decade looks very promising, with a lot of missions and in the angle, and in the Indian scene also. We have been participating in various international projects, 30-meter telescope, square kilometer array, and we are also planning to have our own facilities in the country, and going to the next level of Astrosat 2, or we are proposing for a next future UV mission, major mission. So it is quite bright, and people who would like to do, there are a lot of institutes where you can pursue your PhDs, or even you can go abroad and do PhDs. You can, I mean, many questions, many people come and ask me, do I need to do pure science, or do I need to, can I do engineering? Because various circumstances push me to do engineering. So what do I do? Can I come back and do science? So you can see these facilities, even though at the end are supposed to produce science, you have to build these facilities. And just researchers cannot build these facilities. We need engineers of mechanical, all sorts of engineers are required. And that we do have a huge technical and engineering staff in our own institute who actually build and maintain and run the facilities. Without them, this doesn't happen. Many of those NASA missions, a huge number of engineers work with them. So engineering related to building these facilities are very important. So you can choose engineering or science, still you can be contributing to astronomy through building instruments or doing science with instruments, or a combination. So that is possible. You can take up any research, and one good thing about astronomy is a lot of data are public, and a lot of tools and techniques are available over the internet. And with this, all are installable in your laptop. You can do it, play around, do all sorts of things. Doesn't do anything, it doesn't come and bite you. So just go and explore. A lot of things are there. And you can get in touch with someone you know, ask them for guidance, and you can start working on small projects or certain hands-on training sessions, which tells you that, okay, is it my cup of tea? Do I have to do this? And that gives you a flavor of it, and then more understanding of how things are done in astronomy. It's not pretty pictures. There's a lot of hard work involved as well. Lots of tools, lot of techniques. You need to understand physics and math as well, and of course chemistry. So yeah, it's an interesting journey which you have to taste, and then it'll also give you sometimes you get really passionate about it. So go and experience is what I would like to say.
Yeah, that's a good point to leave. There is a related question to this, so I will just take that question before the other science related questions. So this question says, this is by Swarali. This is how to know that we are good at something, right? Whether she is good at computational things or experimental things, or should she go for theoretical?
Yeah, there are two things. I think there's nothing called good or bad. So what you should be looking at is, do you enjoy doing it? That is more important. Like for me, I can do hours and hours of some kind of work which I like to do. If you put me in some work which is not, I don't like it, I'll just get bored within half an hour, 1 hour. So what you should be, your passion tells you, in your interest comes out alive by the just simple fact that you enjoy doing it. If I have a problem and if I'm solving it and it's not solvable, I cannot sleep. I'll just stay entire night and finish it, and then only I'm able to sleep happily. But if I'm in something which is uncomfortable, I don't like it, I just get bored in half an hour. So as soon as you get a passion, as soon as you like something, you will become good at it. So identify what you like by just doing it, and you don't know, you get drawn into it. That is how you identify your passion. And once you have passion, you will learn and you will become good at it. Don't have to a priori think, am I good at it? No, don't do that. Find your passion and work hard. And if you have found your passion, working hard, you will not realize that you're working hard because you enjoy it, right? So don't think about it. Just start doing it.
Excellent answer. Yeah, that's the thing. Yeah. So yeah, this must be a good message to the people who are going to start their career from Annapurni. Yeah. So there is another question by Basava Raju SP, who is a, I think, different person. Is the space vehicle guided by using principle of gyroscope? If yes, then it needs the knowledge of moment of inertia of the spacecraft. Then how do we measure it?
This is a completely technical question, so I don't know. All I know is that you need momentum dumping. You can't keep going, rotating and things like that. So you need to have, it's to do with the control. So I can't answer this question, but of course you need to have, you can't keep spinning. You need to have, how do they do it in mission? I don't know.
Yeah. Okay. So then, okay, Sarali message, she liked your answer and she will try it out. Okay. So I don't see any more question in the YouTube link. Let us check in the Zoom also. We do not.
I can see only, no, it's not there yet.
Yeah. So, Annapurni, do you want to conclude with some messages to the youngsters, like, or we can?
Yeah, I think I had, couple of questions kind of, I specifically said a couple things. I think it's just go ahead and do it. Yeah. Whatever you want to do, it just, you shouldn't hold yourself back. Just go and do it. That's it.
Good.
Yeah. So
thanks, Annapurni, for the nice talk. Now, Vandana will conclude the talk.
Thank you so much, Annapurni. It was a wonderful talk. It literally took us across the universe, and you explained everything very nicely. And also, it's really nice to see the achievements of AstroSat of the Indian community. And I hope more such exciting things will come. Your words of advice for the youngsters and on how to go about was really useful. And I just wanted to add that the Indian government recently took this Vigyan Samagam initiative for the mega science, as you very well pointed out, that all these big projects involve scientists, theoreticians, engineers, and you can contribute in any aspect. So there are plenty of opportunities. And I think people can read more by visiting web pages and get more information even about everything. So thanks really once again for taking time and explaining all this to the students. And since the talk will remain offline available, I'm sure many more will benefit. Thank you, Bhashwati, for conducting the talk very, very nicely and taking care of all the questions. And so I will I thank all the viewers, both from Zoom and YouTube. And we look forward to you joining us next Saturday. Next Saturday's talk is going to be about neutrinos. It will be given by Dr. Indumati from Institute of Mad Science. So we now will look at universe through a different multi-wavelength spectroscopy you heard. So you will look at universe from something different angle. Thanks once again, and stay safe and stay tuned. We'll be back after the break. Thank you. Bye-bye.
thank you. Bye-bye.